Let's move into chapter 6. Here we're going to cover the basics of exponential functions as well as what their graphs look like, starting with some of the exponent laws that we don't really explicitly teach. So the warm-up is really the only place I kind of go over it. So this is going to be super, super important. Okay. Now, all of these say to simplify. There's a couple different rules. This one is the product rule. And let me show you what happens with the product rule. So let's say that there was like a 4 right here and a 5 right here. I think that helps kind of show the product rule. So product rule, like product suggests multiplication. So the 4 and the 5 will get us a 20. But the thing that doesn't multiply is actually appear in the exponents. The exponents are going to add. So we're going to actually have x to the fifth. So that's important for the product rule. Yes, the coefficients multiply, but the exponents are going to add. Something similar is going to happen in the next one, which we call the quotient rule, which you can probably guess, right? Quotient suggests division. So again, let's do 10 and 5. That means, yes, those are going to divide, but what's going to happen with our exponents is that they are actually going to subtract. So we end up with x to the fourth. It's going to be your quotient rule. So those exponents will subtract when the coefficients divide. Next, we have the power rule. This is where the exponents actually multiply. And again, let's pretend that that was 4, so 4x cubed to the power of 2. What you need to do is make sure that that power gets distributed everywhere. So you're going to have 4 squared x to the sixth, so 16x to the sixth. It's really important that you recognize here is where those powers are going to multiply and not add. Moving along, this is going to be your negative rule. Generally speaking, we don't like to have negative exponents. So the way that we kind of work around that is to create a fraction out of it or to kind of flip it. So in this case, what you could write is 1 over 5 positive power of 2, which would be 1 over 25. The same thing would happen with E, where this is 1 to the negative 2 and 4 to the negative 2. This means we're going to end up with 4 squared over 1, or just 16. Right? So that's going to be also the negative rule. Works both ways. Moving on to the next part, we want to write these with a base of 10. That just means we want the exponent's base to be a 10. So here, I might start by writing my denominator with that base of 10. And then I know, let me actually erase this because I don't really have room. If we want to just write it with a base of 10, we could do 10 to the negative 2, right? Because that would be the same as 10 squared as a denominator. Similar situation here for, I think that's 1,000, that's 3 zeros. We have 10 cubed. But if we want a base of 10 without a fraction, we would make that a power of negative 3. Similarly, we can also work with bases other than 2. In this case, other than 10. Here we have a 2. So 1 over 2 cubed would get us 1/8, and 2 to the negative third would also be the same thing. Here we have 2, I think, to the power of 5, or 2 to the power of negative 5. So just some practice on that negative rule. Next up, let's go ahead and sketch the graphs of x squared and 2 to the power of x. Using a table of values. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, 0, 1, 4. So we're going to have this curve. Oh, that actually almost worked perfectly. There we go. Arrows there. And then let's switch to a different color. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the negative 1 is a half, and then a fourth and 1/8. So you'll notice those getting much, much smaller. Here is the curve, and then 1/2, 1/4, 1/8. You should notice that we are going to have an asymptote at 0. We are never going to get to 0. These will never have a solution of 0. It's impossible. So some differences between them, 2 to the hex has an asymptote. Um, it can't equal 0. The range is limited. In the quadratic, there is no asymptote. The range is also limited. There are no negative y values. Same with the 2 to the x. So just jotting down some things that I'm seeing immediately. You might notice some other things. Feel free to jot that down. But there's some stuff I just saw. Let's look at what the graph of an exponential is going to look like. We've already graphed it. Now we're going to kind of talk about some of the important features of that graph, starting with domain and range. We talked about this back in chapter 3. The domain is negative to positive infinity. It's going forever to the left and going forever to the right. The range, like I just mentioned earlier, is limited. It is limited based on this asymptote. So it starts at 0 and goes to infinity. Obviously, we're not going to include 0 because there's an asymptote. So if we go ahead and jump down here to the equation, that would be y equals 0. Now let's look at that end behavior. As x approaches negative infinity, f of x approaches 0. And as we're going to positive infinity, f of x approaches positive infinity as well. It goes up forever. It does have a y-intercept of 0, 1, because anything to the power of 0 will always equal 1. That's going to be your 0 rule. That is worth remembering. Anything to the power of 0 will be 1. So you always have the point 0, 1 as an option for graphing. Really, really useful for later when we do these transformations. Okay, this is one of the versions for the equation of an exponential. I don't use this one as much in class, but it does come up in the homework. So that's why I do spend some time talking about it. Mm. A is your initial value. B um, is going to represent your growth or your decay. So depending on if you're increasing or decreasing, your B might look different. So I'll talk about that in detail in just a second. And X is equal to your time. Let me pop over here really quick. So if I have growth, let's say by 1.5%, I'm going to have B equals 1 plus the decimal version of that. So that's going to be 1.015. That would be my B value. If I have decay by, let's say, 2.4%, just making things up, B would be 1 minus the decimal version. And I can't do that math in my head. 1 minus 0.024 would be 0.976. So that would be your B value. Okay, that's going to be really important for the homework. So for growth, B should be greater than 1. And for decay, it should be between 0 and 1. And I think it talks about that in one of these questions. B needs to be positive, but it can't be 1. What happens if you have a base of 1 to raised any power? Well, you end up with 1. So there's not going to be any growth if you have a base of 1. So it needs to just be bigger than a 1. If it is greater than 1, it's going to be growth. If it's between 0 and 1, it's going to be decay. So we kind of just hit that right there. So just a quick reminder on that. If we want to solve, you really just need to follow the order of operations. So remember EEMDES, please excuse my dear Aunt Sally. So 5 times 3 to the power of 2 plus 1. You are not multiplying this first, okay? You have to follow your order operations. Exponents go first. You have 5 times 27. That needs to be the order that you solve, okay? If you're putting it into a calculator, it really doesn't matter. You can just put it all in one go. But if you're doing this by hand without a calculator, then exponent must come first. No exceptions. It is order of operations. Same situation here, 5 times 2 squared plus 3. Do not do this first. That is incorrect. Again, the exponent has to come first. So 5 times 4 plus 3 would be the correct order. Just a quick little tidbit there because it happens all the time. I see it all the time. So I want to specify that you need to follow the order of operations here. Okay, let's talk about E. E is what we call continuous growth. It's representative of Euler's number, a Swiss mathematician with the last name Euler first discovered it. It's a button on your calculator. It's kind of like pi, where it's a continuous value. You're not going to be expected to learn it because it literally is a button on your calculator that does that calculation for you. It is represented by this. It is increasing without bound forever continuously. Okay. This is the formula that I tend to use more often in class because it is the more relevant one, in my opinion. We use it in science, we use it in technology, we use it all the time. So I like to use this one more. It still kind of follows similar rules. A naught, this little sub-zero, is what we call naught, NAUGHT. Also not something you need to necessarily know, but in case you need the vocabulary, it's a naught. That is going to be your initial value. Okay. E is that special button on your calculator. K is going to represent your rate. And you can also use R. I really have no preference. If you want to use R because R and rate are easier to remember, by all means. And then T is time, also pretty straightforward. Now, the nice thing with K is that if it's positive, you're growing. If it's negative, it's decay. There's no subtracting from 1 or adding to 1, none of that. If it's growing by 5%, 0.05. If it's decaying by 5%, negative 0.05. It's honestly really, really nice. Now, let's look at these two examples and use this equation to solve. Let me zoom in. Actually, we need to read the problem first. Getting ahead of myself. So, pandas are becoming a species of concern. So, the Denver Zoo is starting a breeding program. They currently have 5 pandas. They're able to get that population to grow at a continuous rate at 1.05% each year. Not super fast, but that's okay. They're taking their time. How many pandas will there be in 15 years at the zoo? We need to start by writing out this function. So, I have A of t equals A naught EKT. Okay, A naught is the starting number of pandas. The rate is 0.0105 t. Okay, so that's the function we're working with. And time is going to be 15 years. So in 15 years, how many pandas will that zoo have? We're just going to plug that into the calculator. I need to open Desmos here because I don't have a calculator next to me. There we go. When it loads, make the text bigger. Let's see. So we have 5, whoops, 5e to the 0.0105 times 15. Wow. We won't even have six pandas, and that's okay. Like, this is just an example problem, but we will not have even been able to successfully have one panda. So I'm going to round up to six for the sake of the example. Ideally, this would have been a bigger number, but I made this up. So it just happens to be that it's a very slow growth rate. I'm going to round up to six and say they'll have six in 1 year. They almost will. Okay. All right. Let me slide this over a little bit. Next question. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams decay to in 3 days? Similar situation, we need to write the function. We have 100 milligrams to start. We are decaying, so negative 0.173 times time. And this is happening daily. So after 3 days, let's see how much we've got. Now, just a quick note. If it's decay, it should be going down. So if you're doing this math and for some reason it's coming up bigger, double check your math. Make sure that you didn't accidentally plug in a positive number. You should have less over time. So it looks like we have 59.5 milligrams remaining. It shouldn't get bigger, right? If we're decaying, it's going away, it's decreasing over time. Right, the next two are practice problems for you, so I would pause this video and then come back when you're done now. Okay, hopefully you paused, so welcome back. Let's go ahead and look at these two problems. We have 50 grams of bacteria in a petri dish. The bacteria grows at a continuous rate of 2.35% every hour. How much will we have in 4 hours? I'm just going to go ahead and jump right in to plug everything in. We're starting with 50. It's continuous. It's growth, so 0.0235. We want to know how much is left in 4 hours. Let's plug it in. 50 e to the power of 0.0235 times 4. We're going to have 54.93 grams. Next, that over again. Now we have radon 220. It's decaying at a continuous rate of 2.1% per year. How much will 1,000 grams decay to in 15 years? Let's find out. We have A of 15 equals 1,000. E, this is decay, negative 0.021 times the 15 years that we're interested in. Let's plug it in. Negative 0.021 times 15. We're going to have about 729.79 grams remaining. Moving on. Now, let's kind of look at some of the other key features that we might need. Okay, you'll notice that there's two things that are currently plotted on this graph. And I like to call those your critical points for graphing. And they're going to be always the same for any base. 0, 1, which we talked about, and 1 comma b, which represents the base of the exponent. It's great. So if you have 2 to the x, it would be 1, 2. If you have 3 to the x, it'd be 1, 3. You get the idea. These are the two most convenient things to plot, so you don't really have to think too hard about it. From there, you can start plugging in other things, but this is really, really easy to immediately put on the graph. Some other things to note, we've already talked about, domain is all real numbers. The range is limited, starts at 0 and goes up. It doesn't have an x-intercept because it's never touching this axis unless it's transformed. We'll talk about that later. And then the one thing that we haven't talked about yet is that it's increasing if the base is positive, and it's decreasing if it's between 0 and 1. So basically, if it's like 1/2 to the x or something like that, it would be a decreasing function. A quick view here on how 2 to the x and e to the x compare. They have a really similar shape. They both still have that 0, 1 as the y-intercept, but notice that e to the x grows slightly faster. And again, that's just because it's continuous growth. Let's talk about transformations. I went ahead and had my parent function drawn of 2 to the x so that I can kind of focus on my vertical shifts and horizontal shifts and all my transformations. So looking at this, it's a table you've seen a million times. It's just a different function. We are going to be moving up one and down one. So we're going to move up and we're going to be moving down. With that, our asymptote also moves. We are shifting vertically, so the asymptote should move up with us or it should move down with us. That's really important. That is going to be the only time that the asymptote will shift for exponentials. So y equals 1, y equals -1. So that's moving up, and this one moved down. Then we have horizontal shifts, which will not affect our asymptote. Just like the others, it goes the direction you don't think it should go. So +1 will actually move left, and -1 will actually move right. And remember that is from solving, right? So that's why this one is at -1. And that's why this one goes to +1. Then we have stretches and compression. So I like to make a little table here of my x value. And then we'll do one in blue. And then we'll do the other one. Purple. 2. My original x values were 0, 1. Oh, I forgot to do my original y values too. Oops. I'll go back and fix that. 1, 0, 1, and 2. A little bit. We'll do y. And then we had 1, 2, and 4. So that was my original function. Now we'll do this one in the blue. This 3 is a stretch of 3, which means my y value is going to get tripled. So 1 times 3 is 3. 2 times 3 is 6. 4 times 3 is 12. It's going to go off the graph, so I can't graph that one. So my new one is going to be 0, 3, and 1, 6, and it's really going to stretch and elongate. Meanwhile, with my 1/3, I'm dividing by 3. So 1 divided by 3 is a third. 2 divided by 3 is 2/3. 4 divided by 3 is like what, 1 and a third? Very small. So now we have 0 and a third, and I've already forgotten the other numbers. 1 and 2/3, and 2 and 4/3. So notice that we are increasing much more slowly. Much, much, much more slowly. Okay. I like to do that little table so you can kind of see where those numbers are coming from. Onward. Now we have reflections over the x-axis and over the y-axis. So here, everything on the y becomes negative. Asymptote does not change, but the range becomes -infinity to 0. That is worth noting. And here we switch axes on the other side. 1, 2, 3, 4. So we go this way. So it is now a decaying function. Domain and range are not affected. Domain and range are not affected. All right. Now, this is where you pause the video again and do some practice, and then you come back to check your work. So pause now. Cool. Hopefully you paused. Welcome back. Now, this tells you we're going to move the function up 3 units. So 1, 2, 3, 1, 2, 3, 1, 2, running out of room, but we'll pretend that that's right there. That also means that your asymptote is going to move up 3 units. So 1, 2, 3. Right? This +3 is definitely a giveaway on where the asymptote's going to be for this question. So let's draw our curve. Moving on. Now we are moving left 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Your curve. Notice I did draw my parent function for everything. I like to do that. I have my 0, 1, and my 1, 2 on all of them. I find that to be the fastest way to get a graph down for exponentials. All right, now we have two transformations. We are flipping over x, and we are moving to the right. So this might be a two-step one for me. So I'll go ahead and do -2 to the x in blue. So we'll flip, and then I will do the next part in green and move it to the right. 1, 1, 1, and there is my action. Sometimes I find this helpful. It's totally optional. If you want to do it in one go, you are welcome to do so. Well, this is one that I think we did in the practice, so it should go pretty quick. I'm going to multiply everything by 3, and whoops, that means this is going to grow much more quickly. Here is the written version of all those transformations. If this is what you prefer, by all means, please feel free to use it. I leave it there for you as a resource, but don't feel like you have to write all this down. And I believe that covers it for this topic.